Next presenter is Christian Roos from Aachen University. Christian, the floor is yours.
Thank you very much for the introduction. I have to apologize up front because initially I wanted to show you 3 examples on sustainable melting and processing of glass, but to be able to go a little bit more into detail and not just to scratch the surface, I decided only to show 2. So if you're interested in the 3rd example, just approach me after the presentation and I can explain it to you. The second thing is, I think I'm a little bit of a rare person here at the Glass Problems Conference because my institute is really dealing with fundamentals of glass. So there are a lot of applications here, a lot of industry-related applications. I'll try to keep you interested, and I will explain you maybe a little bit more in depth about the glass processing. We have about 25 people working on glass, different industry corporations, and mainly we focus on the thermochemistry of glass, forming and melting, and glass ceramics. With that having said, the first example is the optimization of a high-quality art glass. We were approached by a company called Itala, and I think to the Finnish people here in the room, if there are any, I don't need to explain Itala. They're doing very nice sculptures of the Scandinavian nature. I'm not getting paid for advertising for them. I just like the sculptures they are doing. But they're also doing like these high-quality art glass products. And they've approached us with the question to optimize their glass composition. And the specifications they had were in the way listed here, to decrease the coefficient of thermal expansion, so to increase the thermoshock resistance of the glass, increase the mechanical properties of the glass, increase the hydrolytic stability, get rid of antimony, barium oxide and boron oxide if possible, and have a glass composition that can be used both for the automated manufacturing and for the handcrafted products. So you can see the customer usually wants everything. But I have to say it was a very nice project, it was very pleasant cooperation. How did we approach that? Well, the first thing is we did a very thorough evaluation of the process and the status quo at the plant. The second thing is we kept a very close communication with the people on site and especially with the hands-on people. And this is something I cannot emphasize enough because when you're coming from university, fundamental glass science as we do, and you get to a plant and you get to the hands-on people and you say, okay, so we developed a new glass composition. I'm going to tell you what you need to do, how you form your glass, how you melt your glass. Not a good idea. You have to involve the people. You have to tell them what you are doing and why you are doing. You have to get their expertise over 20, 30 years of working with this glass, even though they possibly do not understand the fundamentals of the glass, but they are very important. And also we did quite thorough evaluation of the competitor landscape. We checked the hydrolytic stability of the competitors, viscosity, mechanical strength, and so on. And what we did then is we took all the KPIs from the customer, put it into an algorithm model where we linked the KPIs together. For instance, here like the viscosity behavior with the coefficient of thermal expansion. The model was based on linear or nonlinear incremental methods. And we ran this algorithm and we came out with suggestions for glass compositions that fulfill the KPIs. These compositions were tested in lab trials, like batch free time trials, to screen the melting behavior. And after that screening, we came out with 2 possible options that looked quite promising. These 2 options were taken to large-scale trials, what we call large-scale trials, and we have the opportunity to melt about 12 kilograms of glass in the lab, which is quite unusual for an industry research institute. Not uncommon, but it's rarely, not so often seen. And the way we melt this glass is also quite special because we have crucibles, like you see here. And you put cullet in the crucible, you melt the cullet, and then with these there's no laser, sorry, with these arms, you charge batch on top of the melted cullet. So you mimic basically the industrial melting process. You have a melt and you place batch on top. And then you can evaluate the melting behavior, for instance, for this composition and for this composition, and you can see differences. Also, we did a measurement of the electrical conductivity, and we did I'm not going into deep details with that. We did the typical thermodynamical calculations. How do the class compositions behave compared to each other? And you see these two options. We have evaluated option 1, option 2, compared to the reference. There is basically a little bit of difference in the chemical melting enthalpy, so in the chemical reaction energy. But in the final exploited heat, well, option 2 is a little bit better, but basically the difference between reference option 1 and option 2 is not so big, which means in general that the energy you need to melt these different options is quite similar. And for reasons of the final product properties, it was decided to continue with option 2. And I'm now going to show you some of the results of the real macroscopic properties of this option 2. I'm not showing all results. This would also go too far in terms of time. But you can see here, for instance, the hydrolytical resistance to ISO 719 is greatly improved. So the reference, this is a solution in a sodium hydroxide solution. You see the resistance to the solubility is greatly increased, even better than the competitor, and this enabled us to shift the new class from the hydrolytic stability class 3 into class 2. So this was a significant improvement, class 2 instead of class 3. The thermal shock resistance also was greatly improved. You see here the number of survivors at different temperature differences, so at a different thermal shock load. And you see here at 40 Kelvin thermal shock load, none of the new class composition breaks one of the reference. 50 degrees or 50 Kelvin temperature difference, none of the new class composition breaks 2 of the reference. 60, we are here, 3 of the new and 5 of the reference, and at 70, 4 of the new and even 8 of the reference broke. So this is a significant increase in the thermal shock resistance coming from the decrease of the coefficient of thermal expansion. And all in all, for the first example to sum this up, well, the first claim of the customer was to decrease the CTE and increase the thermal shock resistance. The new class has a CTE of 9.2 ppm times Kelvin to the power of -1, which is better than all the competitor classes and better certainly as the existing or as the previous Itala reference class. The mechanical resistance should be improved. However, the classes we investigated did show quite similar mechanical behavior in terms of, for instance, flexural strength. However, the problem with the old class, so the scratch and edge chipping, is strongly related to the hydrolytical stability of the class. And because the hydrolytic stability was shifted from class 3 to class 2, also the edge chipping was improved. The hydrolytic stability, as I just said, was shifted from class 3 to class 2, and all other classes, all the competitor classes are in class 3. So this is quite a good achievement for the class. And the new class composition doesn't have any antimony, doesn't have any barium in it, and also does not have any boron oxide, which, because of condensates, is a little bit unwanted in the melting process. And finally, also the 5th KPI was achieved, so all the automated products and the handcrafted glass could be formed from the same mass class. So this was a quite, I would say, successful project. The first example. Now, the second example goes a little bit to really the CO2-free production of glasses. And this is a project we call Zero CO2 Glass, and the focus is to produce CO2-free, completely CO2-free, and also soda-free container glass. Can be also transferred to float glass. And if you ask yourself how to get to CO2-free glasses, well, there's first the melting, the processing. And for the melting and processing, if you ask the people, they say, well, yeah, you can use hydrogen-oxygen combustion, you can use ammonia TCR, you can use methanol or methane TCR, you can use full electric melting. So this is, at least, seems to be possible. This is what the response you get from experts. So, well, check. If you ask, okay, how to make the raw materials CO2-free, then leave aside, for instance, lion glass, which has different challenges. Then the people say, well, it's impossible because I have to use limestone, I have to use dolomite, I have to use my soda, and this emits CO2 in the process. So our approach was, okay, how can we get rid, yes, of the CO2 coming from the combustion or from the energy input, but also how do we get away from the CO2 coming from the raw materials? And well, if you just calculate how much CO2 comes from the raw materials, you see about 20 to 30% of the total CO2, depending on the colored ratio, comes from the raw materials. What options do you have? You can increase the colored ratio, sometimes possible. You can use calcinated raw materials, yes, it's done, for instance, for the fiberglass industry, and you can get rid of the soda. Now, getting rid of the soda is a little bit provocative. I hope there's no person from Solvay here present in the room, because they will definitely not like it. But our approach is, we developed a glass composition based on an E-glass composition. And you can see here, this is a general soda-lime-silicate composition with about 12% of sodium in it. And these are options where you gradually decrease the sodium content, even down to 0%. This composition here has 2% sodium in it, but please note, it does mean you don't need to use any soda, because the sodium, if you're down to 2%, can come from the raw materials, for instance, from feldspar. So this option here and this option here are completely soda-free. And decreasing the sodium content gives you a lot of benefits. First, you increase the thermal shock resistance, the mechanical properties get better, the hydrolytical stability gets better, and you save a lot of money, because soda is the most expensive component in container glass and in float glass. So this is approach, and certainly you have to take care of some special aspects. Most people say, okay, when you take the soda out of the glass, you get problems in melting. But if you look at the viscosity curve here, this curve is a conventional soda-lime-silicate glass, and the dotted curves are the developed glass compositions. You see in the melting range, basically, there's not much difference in viscosity. So the glass can be melted in the same way. Also, the energy comparison looks similar. If you get to a little bit lower temperatures, you have to take care for the feeder in terms of electrical heating, because the alkalines are out. The earth alkalines have a little bit worse electrical conductivity. Where the challenge starts is in the forming, because there you can see the viscosity curves separate. So you need to adapt the forming process, and you need to adapt the annealing process. However, these processes are low temperature processes, which means they are much, much easier to handle than the high temperature processes in the melting in the furnace itself. And with that approach, we have German-funded projects from the German Ministry of Climate Affairs with 8 million euro, total 20 million euro project with research and industry partners. And we've just set up a 2.5-ton furnace that is oxygen-hydrogen fired, so completely CO2-free in terms of primary scope 1. And this furnace also will produce the first raw material CO2-free glass composition with the approach I've just previously shown. Yeah, and with that, I thank you. I'll skip that. This is just for the second example. Thank you for your attention.